Oh, wow. Well, good afternoon, everybody. Welcome again to the 10th anniversary of Scala Days. This is a much, much bigger room, bigger stage than I had when I was here 10 years ago. The more people, it's very bright. Someone else mentioned that it's incredibly bright. It's quite hard to see, actually, out of everybody here. Hopefully this time around, I'm also going to be talking about something a little bit more exciting than my topic 10 years ago. Anyway, I'm going to be talking about type class derivation in Scala 3. And I'm kind of reporting on, reporting back on work that I've been doing jointly with Martin and his group at EPFL. I guess I've been working on it more or less full-time since October. But it's also a kind of a continuation of other work that I've been doing with work on Dotty, work with the Scala compiler team at Lightbend, basically trying to make the Scala 3 future safe for the kinds of things that people have been using Shapeless for in Scala 2. Given the fact that things are going to change so much in Scala 3, Shapeless makes this fairly essential use of a ton of macros, which, as we now understand, there's really, really very little prospect of those things carrying forward across the gap between Scala 2 and Scala 3. I've also used this process as being a fantastic opportunity to really just sit down and take a completely fresh look at how type class derivation should work in Scala. Reevaluate some of the decisions I made in Shapeless. I mean, it's been around for quite a few years now. There are many, many things that, with the benefit of hindsight, were not the greatest ideas, and it's a wonderful opportunity to basically have a chance to start again from scratch. So it's a great opportunity, and I think I'm very happy with the way things have gone. I mean, obviously. It's not really for me to judge. It's really for the people who actually end up using this stuff to decide whether or not I've been successful. But certainly, I had a ton of long-standing open problems in Shapeless it took me a very, very long time, perhaps longer than maybe was reasonable, but I mean, it's certainly taken me a long time to actually get my way to somewhere really satisfactory with them. But I kind of feel like I've got there, so I'm quite pleased with the result. I was also very interested to see that when Martin did his sort of informal Twitter poll of, most eagerly anticipated features in Scala 3 for expert programmers, that type class derivation came out top. And there's kind of a couple of conclusions I draw from that. I mean, one of them is obviously that type class derivation is something which people find very interesting, and are presumably trying to do. The other conclusion I draw is that they find it quite difficult at the moment for a variety of reasons, and they're probably using Shapeless to do it, which suggests that, for all that Shapeless solves a bunch of problems, it brings a bunch of its own problems in its wake, and people are probably quite, I won't say necessarily desperate, but we're quite keen to see something happen in Scala 3 that makes their lives easier. So, and again, hopefully the kind of stuff that I've come up with will ease some of the pain that people feel. Anyway, without more ado, here we go. Type class derivation. What is it? Well, I kind of assume that most of the people here know what it is, but just a brief reminder. Type class derivation is a mechanism for automatically inferring type class instances for algebraic data types based on the structure of the algebraic data type and given instances of that type class, or perhaps related type classes, for the component parts of the algebraic data type. So here's an example of the kind of thing we're talking about. Suppose we have, a show type class, the show type class from cats, or something similar. We have a case class, imaginatively named ISB because it contains an integer, a string, and a Boolean. a simple product type. We have instances for the components of that type. So we have we're assuming, I suppose these should be delegates now, but anyway. We're assuming that we have instances available in scope for show for an int, a string, and a boolean. And then what we're saying is that we would like the compiler to help us synthesize a sensible show instance for ISB based purely on the structure of the type and the type class instances for the components of that type. So we should be able to summon an instance of show ISB without writing any more code. That's the essential idea. Okay, so the way, I guess, backing up a tiny bit, the way people address this in Scala 2 currently is using libraries like Shapeless that will help generate, help automate the process of doing that. So what is Scala 3 going to bring to the table that either improves on that or replaces that or whatever? So the way that Dotty and Scala 3 are going to support type class derivation is via a combination of a small number of compiler-supported primitives. These are sort of primitive types and mechanisms. We have a type called mirror, which plays a similar kind of role to the one that generic plays in Shapeless. We have Derives clauses. These are ways of annotating algebraic data types to say that the consumer of those data types would like instances for some known set of type classes to be, as it were, pre-computed and made available in a cached form, I suppose, without requiring sort of recreation at each occasion where they're used. And the third component, which interacts with the first, is a sort of a convention-driven mechanism whereby authors of type classes can opt into a mechanism enabling those Derives clauses to compute instances of type classes without having to go directly through implicit resolution mechanisms. So those are the compiler-provided components. As I mentioned, they're very minimal. We'll go through them in a little bit more detail in a second. They aren't, I think, although Martin has been sort of demonstrating he showed in his keynote yesterday evening, he showed how one might go about implementing the derived method for a type class on a type class companion object, using a combination of Dotty features, in particular inline matches and implicit matches. It's probably something you wouldn't want to do by hand. It's quite because the mechanisms are provided are really quite low level. You end up certainly you would have to write quite a lot of code yourself. That code, it's taking one particular kind of stance on what kind of goals you might want to have. So it uses aggressive inlining, which in some circumstances could produce very, very efficient instances, very high performance code. On the other hand, it produces a lot of code, and a lot of code is often not a good thing. This isn't necessarily the approach you want to take. It requires a lot of work by type class authors, type class library maintainers, and it has a certain amount of at least overhead in terms of bytecode footprints and such like. So the other component of type class derivation for Scala 3 is going to be provided by third-party libraries, and sort of in conjunction with working on the type class derivation primitives, I have also been working on a version of Shapeless 3, currently only the type class derivation components, making use of these facilities. Partly as a demonstration that you know, the facilities we're baking into the language, baking into the compiler, are actually good enough to do the job well enough. But also, you know, because these are primitives, we won't be wanting people to use these things directly, to have something available that people can start playing around with as soon as possible. So it's a preview, it's on GitHub. We'll get to a link a bit later. Okay, so what do we get? We get mirrors. So that was the first component of the compiler support that I mentioned. So a mirror is it's a generic programming primitive. It's a compiler intrinsic for Scala algebraic data types, by which we mean sealed traits and case classes, but also enums. I mean, there is really no difference in terms of support between sealed traits and case classes and enums in this respect. And crucially, and this is the thing that I'm personally am quite excited about. It supports algebraic data types of all kinds. We'll see what that means in a second. This has been something which, in my opinion, has sort of caused Shapeless's ongoing development to sort of grind to a halt well over a year ago, I think, trying to wrestle with exactly how to deal with that now. So this represents, from my point of view, real progress. And as I mentioned, it's intentionally very low level. So what do you get? So the mirror type is essentially really, it's a bag of types and one method each for each of some types which correspond to sealed traits or the top level of an enum, and one method for product types. So the types that, and roughly speaking, you can imagine these things being implemented by the companion objects of the sum of product types. So for example, if we have a case class has a companion object, we would expect a case class to implement the product trait that you can see at the bottom of the slide here, a sealed trait, well, a sealed trait doesn't automatically have a companion object. An enum, on the other hand, does automatically have a companion object. So we would imagine certainly the enum, well, it is the companion object. We would imagine the enum directly implementing the mirror sum subtype. So well, let's see what these things are. So let's have a look. So here is our int-string Boolean case class. So what we get from this as a combination of things which are provided by the case class companion and also things which are, as it were, synthesized by the compiler when you actually ask for an instance of the mirror at a call site for a particular type, is you get a value of this product mirror.product type, and it contains a number of types. The type you're going to ask for it by is the mirrored type, so this is the type I'm requesting a mirror for. And you can see this is done via a type refinement. There is this thing called the mirrored monotype, which will become a little bit clearer what that means in a slide or two. And then we have a number of things which look maybe kind of slightly peculiar, but what we have are types corresponding to the name of the type. So this is a singleton string literal type. And also a type corresponding to the labels of the element. As you can see, we've got a tuple here, and it's a tuple of the string literal types I, S, and B corresponding to the labels of the elements of the type. Now, what the rationale for making these type members rather than value members is footprint. These things are types. They leave no traces in bytecode. Well, except maybe apart from Scala signatures. But in terms of bytecode that has to be loaded by a JVM when you're running code, there is nothing there. This is all stuff which is consumed at compile time. So the idea here is then that we are going to be, if we need them, using type-level programming mechanisms, the sort of Scala's sort of near-dependently typed mechanisms to sort of bridge the gap between something which is represented by a string literal type and an actual runtime value, which we can use mechanisms provided by the compiler to give us one of those. The other crucial component is the element types. So you can see here this is a tuple. So for our ISB type, which contains an int, a string, and a Boolean, the element type is itself a tuple of int and string and Boolean. people who've played around with Shapeless will recognize, immediately see there's a bit of a difference. There are no H lists here. These are just tuples. It turns out that we really just don't need to have any kind of specialized representation for these collections of types. Tuples are just fine. I mean, they're perfectly good things for representing essentially a list of types with some kind of order. Okay, so that's for a single, simple product type. Well, what about something a bit more interesting? So here we have an ADT. It is both polymorphic, and it is a sum of two products. So obviously this should remind you of option from the standard library. And if we have a look here at what the differences are between what we saw on the previous slide and what we saw on this slide. So here, the mirrored type is opt. Now, if you've not seen the way things work in Dotty before, this may look a bit odd, because previously I had type mirror equals and then a fully applied type. Here I have mirrored type equals opt. Opt itself is a higher kinded type. It's a type with a type parameter. So the key thing we have here is that this mirrored type member is in effect polykinded. It's strictly speaking, it's not. In principle, it could be defined on the mirror trait we saw earlier with a bound of any kind, which is the way that kind polymorphism has been added to Dotty. It turns out it's actually not necessary, and in fact, this is something that you can model in Scala 2. And effectively what we're doing is we're just refining the mirror type with a new type member, and we're allowed to specify, in effect, the kind of the type member as we refine. So here, again, as well as seeing that difference from the previous slide, we can also now see a difference between mirrored type and mirrored monotype. So mirrored monotype is essentially the existentially quantified version of the mirrored type. So it's basically what is the most general type, the most general fully applied type that you can get, given that you have a higher kinded mirrored type. So that's basically we're plugging the holes, and this is used. If we go back a few slides, you can see that the two methods, the concrete methods which are defined on values of the companions of the sums of products, are defined in terms of mirrored monotype. I'll come back to exactly what they mean in a second. So you'll also see the main difference here, as far as the main remaining difference here, is the fact that our element types are now defined in terms of a higher kinded type definition. So here you can see that there is using the new double arrow to represent a type lambda. So here the element types are now has a type parameter. And what you should see is that the type parameter of the algebraic data type corresponds directly, so its kind, the kind of the algebraic data type corresponds directly to the kind of its representation type. And this is a really crucial component of getting the generalization to multiple kinds working nicely. Okay, so that was if you like the roots, the sum part of the ODT. If we go on to the first of the product branches, you see that, again, this has the similar structure to the previous one. And again, we have this distinction between mirrored type and mirrored monotype, because again, it's polymorphic. And you can again see here that the element types is also a type lambda, again, with the same kind corresponding to the type constructor. And you can also see that the monotype is different from the mirrored type. And again, oops, yes, sorry, I've just done that. And again, for the nothing type, sorry, the none type, this is basically it is a product type. It's a special case for singletons, but it's still a product type essentially. And of course, this is not polymorphic, so it's the same as the monomorphic product case here, effectively. So those are our mirrors for, if you like, the natural mirror. So in other words, the mirror which corresponds directly to the kind of the type that it's a mirror for. But you might also be wondering, well, there are lots of things that you do with type classes where, say, for example, you want to define a show instance of a type class for option of int. Well, here we've actually sort of plugged the hole in the type. So you might wonder how that's going to work. Well, we can also ask for a mirror for our type constructor applied to a type. So here we have the mirror for option of int. And here you can see, actually, now it's suddenly lost its polymorphism as far as the mirror is concerned. Mirrored type is option of int, so it's a fully applied type of kind star. Mirrored monotype is now the same again, because it's also fully applied. So this looks much more like the mirror that you got for the ISB case class than it looked like the polymorphic case before. Okay, let's have a quick look at some of those and see what we get. So here, you can see we have the int string Boolean. If I just quickly compile this, this is going to spit out the trees that the compiler is generating as it does its job. Do I have a laser pointer here? I do. Wonderful. So can we spot what's going on here? So here is here's the companion object for ISB. You can see that it extends mirror.product. And you can see that it defines the fromProduct method. So fromProduct is going to take an arbitrary product. Remember what I said about this being low level. This is low level and somewhat weakly typed. So it's going to take a product, essentially a tuple, and it's going to give you back a value of the monotype. So the mirrored monotype here is ISB. So really, it's just doing the obvious thing that you would think you would do with a product, pulling out the elements, casting them, stuffing them in the appropriate places of an ISB constructor. Now, remember, of course, no human writes this code. This is essentially a sort of partially erased rendering of the code that's generated by the compiler. So if you're worried about this not being well typed enough, don't. Okay, and so that's shown some aspects of it. If we now have a look at what happens when you try and summon an instance of it. Here, what we can see is, well, there's a bunch of stuff. So one of the things you're seeing here are sort of interesting kind of artifacts of the way that the inline Scala Dotty's inlining mechanism works. The details don't need to bother us right now. But anyway, here you can see we're getting back a value of this mirror type. Here we have the mirror monotype filled in, we have the mirror type filled in, we have the label type filled in, we have the element types filled in, we have the element labels. So now you could start using this thing to do sort of type level computations to realize some of these type members as actual runtime values. Now, the one interesting thing to see here, hopefully it's visible, which is just down the bottom, is that, in effect, what we're actually getting is the companion object. This is the companion object. This is a reference to the companion object of ISB, essentially just cast to that value. So we're basically taking the companion object, we're superimposing the interesting generic programming type on top of it and yielding that as the value. And that's kind of crucial because it means there is no additional runtime cost of having these things around compared to just what you would have with a vanilla case class. And this is definitely from a kind of runtime footprint point of view a big win compared to Shapeless. So now we could also have a quick look at bear with me a second. The polymorphic case. So let's have a look at that. So here, again, you can see that we have a where is it? Okay, so here we have the mirrored monotype is now the existentially quantified, the wildcarded main type constructor. And now you can see what we actually get for the definition of ordinal. So that, again, this is a method which is defined on the companion object of opt. This is the ordinal method. It takes an argument of the mirrored monotype, so essentially an existentially quantified option type, and it does a match on it, and it will give you back an ordinal corresponding to which path, which branch in the ADT you've taken. And so between those two things, from product, for product types in case classes, and the ordinal method for sum types, seal traits, or enums. Basically, these are the primitives you need to actually do all the work. Actually, that's not quite true. We're also going to use things like some of the sort of rather old-fashioned sort of product iterator stuff from the product type. Again, these are low-level primitives. They're not intended to be used directly. There will be a sensibly typed veneer placed on top of them, and that's where we're going to get to shortly. So again, I'm just going to very quickly show you what we get for. I'll show you two cases actually. So I'll show you what the summoned opt looks like. So here you can see opt with the various additional components filled in. So we've got the label, we have the full element types as a type lambda, and we have the labels of the individual branches. Now I'll also show you what we get when, instead of doing that, we actually try instantiating this thing. So what we've done here is we're now asking for the thing opt instantiated at int. So now we get the mirrored monotype and the mirror type are the same. They're both option int. It's now monomorphic, and our element types, again, we now have just a simple monomorphic tuple of some int or nothing. What was I going to say about that? Okay, that's it. I'll park that. Okay, so back. Right, so the next thing is the derives clause. So let's have a look at this. So derives clauses are annotations that can an ADT author, the author of a data type, can add to the declaration of their sum or product type. The compiler will see that as a request to generate instances for the specified type classes directly in the companion object of the data type you're defining for. So here we have our now familiar ISB type. We're referring to the show type class that we had right at the beginning. This is the companion of the show type class, and we define, assuming the type class author wants to opt into the mechanism, we define a derived method. The derived method is polymorphic in some type T. It's handed a mirror of T, and it promises to give you back a show of T. I'm going to leave this blank for the second. So what does the compiler do? Well, the compiler, in the companion object, is going to, as well as having ISB extending the product mirror, it will also provide a definition of basically the instance we would be asking for. So in this case, show of ISB. Oops, I left the type parameter off there. That's a mistake. And it does that simply by calling, compiling a right-hand side, which is a call directly. It's not implicit. There's no implicit search. There's no implicit search involved in here. It directly calls the derived method on the companion of the type class trait, providing itself, because it itself is actually a mirror, as the argument, and it relies on the type class companion method delivering back a suitable value to put here. People who actually want to look at this stuff, I may show you just in a second, will notice that currently this is defined as a def rather than a val. That's a bug in the implementation right now. So let's have a look at that quickly. Um, so let's see how that looks. Okay. So here you can see basically what we've got. So here is our show. Here is the show member. As I mentioned, this is a def. It should be a val. It's a show ISB. It has been produced by calling the derived method on the show companion, which I'm not sure that's visible here, but it's not very enlightening because I think it's implemented as triple question mark, and that's, yes, it is there, just up there. Oops. Lost it just there, for reasons we will come back to. So it's a call on show derived, handing itself as an argument, and we're assuming some magic happens, and we'll get the right kind of value. So before I move on and show you what that magic might be, I just want to show you one other thing. Actually, no, I will show you one other thing first. I'm going to show you this. So now if we say, so this is some use in the code. So this is some call site where we've requested the show instance for ISB. What you see here is this is the result, again, of inlining. A lot of these things are inlining artifacts. You can expect these things to sort of disappear. But basically, you have what is, in effect, a direct reference to that member of the ISB companion object. So in terms of caching these instances, not producing them repeatedly, not duplicating them, this is really, really very nice. This is completely subsuming all the functionality that we had with things like cached implicit and shapeless. Okay, so you might ask yourself, as I kind of alluded to earlier, what happens in the case of a polymorphic type? So let's have a quick look at that. So it's the same show. So what does this do for us? Right, what does this do for us? Well, what do we get? We get a derived show. But now this is interesting, and it kind of, you think about it, it has to be the case, because option, which is what we were deriving for, is a polymorphic type. So it has a hole in it, and so we can't produce a single value corresponding to show for option, because we need to somehow or other fill the hole for the T, which is polymorphic in show. So what we actually get in this case is this is correctly a def this time. We have a derived show, which is now polymorphic in T, and it will take an implicit argument, which is the show for the parameterized element of type T, and then it will give us back an option of T. And again, this is done in terms of a call on, where is it? It should be here somewhere. Oh, here, right, okay. Right, so in fact, what's happened here is it's actually completely inlined the implementation of the show method. There's a triple question mark here. But actually, it may be easier to see if I remove that. Yes, let's get rid of that. Let's do that again quickly. And now what you can see is that, yes, so this is now the definition of derived show again, but here you can see now that it's not inlined away to nothing, you can see that we've got a direct call on the derived method, again, taking the mirror, but now it is parameterized in terms of T. We can kind of see that in action if we look at what a use site might be. Do we have, yeah, I'll uncomment this as well, otherwise it wouldn't compile. So now you can see the use site here. So what we've got now is effectively a direct call on the method in opt. This is the opt companion. We're calling derived show, and it's filled in the instance argument for show, which is the type parameter for int here. So obviously we get a new value each time, but clearly any infrastructure, any boilerplate code which has had to be generated to, as it were, fill out the surrounding structure around this int instance, that's only ever been done once. So that's been done once, computed once, and now all we're doing is summoning a value by applying a function to an instance for the parameterized type, which is is optimal. I mean, I don't think you can't do any better than that, basically. Okay. So here we go. How long have I been going? Okay, that's good. Right. So I showed you some triple question marks, and up here I put dot dot dot, and well, what is that dot dot dot? Martin showed you one possible way to fill out that dot 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 by defining things directly in terms of inline methods, computing directly over mirrors. I personally think that's too much to ask people to do. I think it's a good demonstration of the power and flexibility that this mechanism provides, and that Dotty's more disciplined metaprogramming facilities allow you to do. But I don't think its ergonomics for a typical author of type classes is particularly good. So in conjunction with doing the work on designing the mirror and derives mechanisms, I have also simultaneously, as I mentioned, been designing the next major, essentially, rewrite of Shapeless 3, and this is kind of what we're looking at. So Shapeless 3 has a generic type, which corresponds to the generic type that exists in Shapeless 2. However, it is completely polykinded. So Shapeless 2 has sort of a very half-hearted and sort of slightly confused attempt at handling two kinds. It handles kind star, so fully applied types, and star arrow star, so types with a single type argument. And it's really quite ropey the way it works. There's huge amounts of duplication and lots of really horrendous, gnarly macros. It's not very nice. Getting rid of all of that mess has been one of my major goals with this redesign. The new design is completely polykinded, and all of the duplication that I had to endure in Shapeless 2 is gone. It's implemented directly in terms of mirror, so it actually turns out now that generic is actually essentially a type alias for a refinement of the mirror type. So it really is directly defined in terms of mirrors. Now this gives you a facility which is essentially equivalent to a polykinded generalization of Shapeless as it is now. To work with it, you would need to work with similar kinds of techniques that you work with Shapeless 2. So this has pros and cons. On the one hand, it's very, very general. You can do basically anything with it. On the other hand, you end up with lots and lots of folds. You have to work with an explicit representation type, and it can be quite complicated to work with. There are some sort of mitigations in Dotty, in as much as some of those folds can be, well, in fact, all of those folds, they no longer have to be implemented in terms of sort of the logic programming style implicits. We can work directly with inline functions, specializing inline functions, which means that many of those kinds of recursions can be captured in code which looks like normal functional code. But even so, I think that is still not something that people typically want to do if there are simpler alternatives. So one of the things, and it also has the downside that it involves a certain amount of, it involves a significant amount of inlining, which means that you have code generation, which means that, say, your instances in your companion objects are large. So we want something which is much, much more compact. So I kind of looked at seeing if I could come up with a scheme which would basically do the optimal thing for type classes which fit into a particular kind of regular or monoidal kind of pattern. So type classes where basically if I've got a type which has components A, B, and C, it can be defined in terms of instances. A type class instance can be defined in terms of instances for those component types. This can be done in a much, much, much simpler way. For that subset of types, there's a number of sort of standard folds and fold-like operations that are, I think, pretty much adequate for most purposes, and capture a very, very large proportion of the territory. It's implemented in terms of generic. It's consequently polykinded in exactly the same way that the generic is due to its extension of mirror. If you were to squint at the kind star case of instances, product instances, and co-product instances, you would see something that might remind you a bit of Magnolia. And it was I think, an accidental discovery, but it turns out that something a little bit like Magnolia actually works in the kind star case. So you could think of it as being a polykinded generalization of that. Okay, so what do you get? So this is generic. This should look very, very similar to people who have worked with generic and shapeless. We have a product generic. It works in terms of mapping from our base type to a representation type and back again. It works both for products. It also works for co-products. The difference here is that our representation types are actually now going to be straight tuples. There's no H-lists anymore here. In the case of, if you remember that for the sum types, they were also represented as tuples of types, rather than sort of nested ithers, which is what Shapeless's co-product type is. That's now gone. What happens is we can use a dotty match type to take a tuple of types and turn it into a union of types, which is actually something that works really very nicely in this context, because then we end up with the from and to representation methods of generic for co-product are basically identity functions, which is really quite neat. So this is kind star, so this corresponds to types like our ISB type. For kind star arrow star, it's basically the same. But you can see, obviously, now that we have additional type parameters threaded through. This was the thing that was basically causing me to, as you'll see from the next slide, when we get to kind star arrow star, things start getting painful. Then we now have the table flip kind. So the kit of parts that ships with Shapeless 3 is you get support for kind star, star arrow star, star arrow star, star arrow star, arrow star, and star arrow star arrow star. So we can basically do these out of box with a certain amount of boilerplate, but it's very simple. It's comparatively simple mechanical boilerplate, and as I've said here, you know, if you need a kind which doesn't ship by default with Shapeless, it's fairly straightforward to add it anywhere in any library or send me a pull request or whatever. Anyway, in terms of what do you get with generic, as I said, it's refinements of the mirror types, the to-repr and from-repr stuff that are per kind extension methods. So this is using Dottie's new extension mechanism. And the reason they have to be done that way is because there's simply no mechanism available to abstract over those differences in method type signatures, including the different number and kind of type parameters on the from and to method. So there's beyond, I mean, maybe in a future version of Dottie, maybe in 3.1, we might go for a more full-blooded version of kind polymorphism, which would allow us to abstract over those signatures. But I think that's That's step too far for 3.0. And I think we can wait for that. This is good enough for now, I think, and it will give us a good sense of what's actually needed. And as I said, yes, and so even though these methods are obviously distinct and the signatures can't be unified, it actually turns out everything erases the same thing, because ultimately we're turning a value into a value, and the signatures, they all go away, they all compile away. So we can actually implement the whole thing in terms of what I've been calling an erased kernel. So it's basically a kernel of Shapeless where everything is channeling akka any to any. But you never get to see that because you only get to interact with it via a per kind fully typed veneer. Okay, so instances. This is the sort of the slightly Magnolia flavored thing. Captures common folds. It will pretty much completely eliminate implicit induction boilerplate for these regular monoidal type classes. It's implemented, as I said, in terms of generic, so it has the same kind of polykinded structure. It's also implemented in terms of an arrays kernel, which means you have no code duplication, which is great. So it means we keep our footprint, our bytecode footprint, absolutely minimal. So consequently, it has excellent compile time performance, and bytecode footprint is small. That's very, very good. It means our load time. If you're generating something a very, very large ADT, you could pay a significant cost just in terms of bytecode verification time, loading a very, very large, massively inlined generated derived instance. As I said. Well, I think I basically covered that. So there is some work being done. So there's some work being done by Nicola and Agalos, anyone? Olivier as well, on doing a version of this in terms of staging. One of the things we're going to do at some point is try to sort of evaluate what the pros and cons of more aggressive inlining versus this kind of model are in terms of runtime performance. Okay. I think I'm beginning to run out of time. I always do. So these are the kinds of folds you get for products. These are the kinds of folds you get for co-products. Don't worry, I will explain a little bit when we get to some signatures. So I've only shown you the stuff for kind star. But basically, both products and co-products, you can define a mechanism for if you can define a mechanism for computing a value of your t from type class instances here of the components of t, so that could be the elements of a case class, or it could be the branches of a sum type, and a value of one of those elements, then you can produce a value of the whole type. So possibly an interesting thing you'll notice here is the use of a polymorphic function type, which is another new addition in Dotty, which makes a lot of this stuff enormously easier. This produces really very, very simple type signatures, as we'll see in an example in a second. For products, specifically, you can construct a value. If you can construct values of all the components, and that's what's essentially happening here. You can unfold a value. So if you've got some sort of seed, you can unfold it. If you can construct a value which sort of consumes bits of the seed and, say, an instance for some of the components of the product type, and you can then, at that point, possibly get back an instance of the type and maybe some partially consumed seed. This is something which is useful for doing deserialization. We're constructing a value of a product type by sort of nibbling away at bits of say some input, and producing a value, possibly an optional value, and maybe some additional continuation of input. Map2, that's the kind of thing you want to do if you're, say, trying to combine a pair of products like you would in a monoid. Fold left allows you to sort of compute a single value from a single product. Fold left 2 allows you to compute a single value from a pair of products. And this is the kind of thing you might do if you're computing, say an EQ, an EQ type class instance. You'll notice that both of these things have this thing called complete OR. I don't know if that's necessarily going to be a permanent fixture, or if that goes somewhere else, but this is essentially something which allows you to compute a value and either continue or just say we're done. So this allows you to do sort of short circuit evaluations. If you're computing eq, you can stop as soon as you see the first difference. For co-products, things are slightly different. Here, although they coincide on map, both products and co-products can both support this map thing. You can project out, we've got this branching structure. You can choose one way to go and some kind of seed value, and then you can provide the thing with a function which will take the seed value, an instance for that branch, and then compute a value. So again, this would be something you might work with for doing a deserialization framework. And then fold is something which is essentially going to collapse the branches, pick the branch which is actually realized, and give you the realized value, the corresponding type class instance for the branch, and allow you to compute a result. And fold 2 essentially says, if you have two co-products, they both align on which branch they're on, then you can compute a value from them. And that again, you would use that in the context of something like eq. So that's essentially the shape of the instance types for chi-star. I'm not going to show you the generalizations of those because obviously you can imagine every single one of these things is going to have additional type parameters threaded through them. It ends up looking very, very ugly, so I'm not going to bother to show you that. I'll just quickly show you an example of a type class defined that way, and then wrap up. So here's monoid. So most of this is just the standard boilerplate you would expect to have anyway. So we've got, that's the type class. We have instances for a bunch of primitive types. Here is the hook that a derives clause, a dotty derives clause, is going to call back to. Now, if you remember on the slide, I showed it being parameterized in terms of mirror. Well, product generic actually just is a mirror. It's just a refinement of mirror. So this is a perfectly acceptable signature for derived. Any other type class derivation framework that wanted to do the same thing, as long as they also refine mirror, they can also fit into the framework in exactly the same way. This is very nice. All it does is it basically says, you've been handed a generic. I can turn that generic into one of those instances types, and then pass and then call an instance here, non-inline now. So this is just vanilla ordinary code, and I can now define the monoid instance generically using the folds, the maps defined on the instances type that we saw earlier. So I can construct a value of type T if I can construct values from monoids for the elements of T. Similarly, I can combine two A's if I can combine them element-wise. And it's just, and that is now a one-liner, a very, very simple one-liner for doing the derivation. This would be much more complicated to write in terms of inline methods in Dotty. This is, I think, very, very similar to what you would get using Magnolia currently. I think it's not very different from that. It's probably more concise because of the way that it uses polymorphic function literals here, which I think help a lot. And obviously it hooks in very nicely with the infrastructure. And eq is another good example. So this monoids only have instances for products. This has products and co-products. So here we have a similar kind of derived clause. We get handed a generic. This time it's neutral, whether it's a product generic or a co-product generic. We have a little bit of infrastructure which decides whether we're going to follow the product or the co-product branch. But essentially, it's kind of what you'd expect. So for a product, we're just doing a fold, starting with true, and then we'll just continue, and we'll either bail out with false early, or we'll continue with true until we've exhausted the structure. And for the co-product type, well, basically we just follow the one single branch. Well, if we're handed two values, if the two branches align, we'll compare them element-wise. Otherwise you get otherwise it's false. So something a bit more sexy. So this is basically the state of the art with Shapeless 2. So deriving type classes for types of kind star, arrow, star. So that's our functor type. Sorry. Oh, okay. I'm over time. Never mind. I'll just show you anyway. Whoops. It's a break next, isn't it? Is it a break next? Can someone tell me, is it a break? Would you like me to carry on or shall I stop? Carry on, yeah? Okay. I've lost my place now. Here we are. Okay, functor. Right. Okay, functor is really cool. I'm really excited by this because there is a huge amount of stuff in kittens, which is a type class derivation for cats. It sort of does as much as it possibly can with the sort of the attempt at higher kinded stuff in Shapeless at the moment, and it derives functors, but it's just so much more complicated than this. And this is just so we've got the derive clause. Make instances, products and co-products coincide for functor. I guess it's kind of unsurprising that they would, but basically you just map over the instances for the components. That's it, you're done, which is just awesome. And then it also turns out that there are these other things like higher kinded functors, functor k. How about that? So which is a something which is a type parameterized in terms of a higher kinded type itself, and then you map over it with a natural transformation, so something like this. So this is well beyond Shapeless's capabilities. And hey presto, it's identical. Look at that. We just map over with a single one line, mapping over. We get handed the individual type class instances for the elements of the higher kinded type, or type with higher kinded elements, and you know, it's just the same. It's lovely. It's absolutely lovely. Okay, so one last thing I want to show you is an example of something which is not possible to represent using the sort of the regular stuff. So this is something that is currently, I guess, a USP for Shapeless, and I think will continue to be a USP for Shapeless 3. So this is a transform type. And basically, this is something which will allow you, say you have a pair of case classes, they coincide on some fields by type and name, and you essentially want to extend the smaller one to the bigger one by filling in, possibly permuting the elements if they're in different orders, and then filling in components with stuff drawn from a monoid, say, for example, as a default value. And this, I'm just going to show you this chunk, really. So I sent, oh, okay. Whoops. I shouldn't have pressed that. Yes. Oh, no. Control I. G. So here we're just, so this can't quite fit in with the Derives infrastructure, but it doesn't really matter that it doesn't. It's not something you would necessarily expect it to be able to. But you can basically hand it a pair of generics, one for each of the types. So this is why it can't be modeled as a regular type class. But then we can essentially merge the two corresponding records. So this is making use of the labels. So we're making use of the element labels. So this is the kind of stuff that you would do in Shapeless's labeled generic. We can write code which actually looks much more like real code than the stuff that uses implicits in Shapeless 2. We can merge the records and then just tip the record back into the expanded data type and get a value, which is just very nice. Okay, that's enough examples. I will wrap up now. So that was that. So what's next? Backport to 2.13, 2.14. Believe it or not, I think it's possible. So it doesn't depend on any of Dottie's polykinded kind polymorphism stuff. It's done with refinements. That can be backported. The additions to companions are really tiny. You know, if you compare them to the amount of stuff that's generated by case classes in general, the additions are really minimal. So I think it's small, it's low risk. It's mainly adding half a dozen type members references to companion objects, which is really no big deal. So the fact that it's minimal is a real huge help to doing that. Then backport Shapeless 3 itself to Scala 2, either if in terms of a backported mirror or in terms of Scala 2 macros, and that's fine. So then maybe a compatibility layer that will help people get from Shapeless 2 to Shapeless 3. And then we have a migration path to the DOSI, which is kind of what I've been trying to get at. So the path is kind of start by moving from Shapeless 2 to Shapeless 3 on Scala 2, 13, or 14. And then, having done that, you're in a good position to move from Scala 2 to Scala 3 if you're using this stuff. Okay, other things, sort of more administrivia. Shapeless is going to move to the type level GitHub organization. The artifact is going to come out of com.chusai and go into org type level, which it really should have done a very long time ago. Amongst other things, it enables a much larger pool of maintainers and publishers to work on the stuff without me being necessarily the bottleneck. You can find the preview here. And, well, I've blown my budget. Is it still a break? If people still want to ask questions, then I'm happy to. You want to wrap up? Oh, okay.